So I'm going to be working on some x86-64 code gen today, and my basic sort of thought on this is that I'm going to have a generator type that will know how to emit machine code bytes, and then I'll match those up with IR instructions a bit later when I sort of link the two together. So I'll start by basically just organizing everything into this code gen folder. So I move IR into there. And anywhere that uses IR needs to now use code gen. And then in this code gen folder, I'll have this x64 package. And what I was thinking of in here was to have some globals that describe operands. So we'll have some operand type, which will be a struct. And we'll have info on here, which will be an int64. And we'll have a value. So this could be, for example, the immediate or the register number. And then info would hold stuff like whether it's a register or memory, things like that. So for example, we'll have a bunch of variables. We'll have AX, which will be an operand. This would be a register, and it would be the value 0. So AX is register number 0. The register numbers we've seen in the Intel docs before. For example, in Appendix B here, they describe the registers down here. So for example, AX is 0, then CX, DX, BX, SP, BP, SI, and DI. And then if you extend these with, a REX prefix here, these become, R8 all the way down to R15. So we're just going to have, we're going to list all of them and just give them their numbers here. So this will be CX, DX, and BX. Then we'll have SP, BP, SI, and DI. And then we'll have the extended registers, which are R8 all the way down to R15. So this will be F, E, D, C, B, A, 9, and 8. And then these ones over here will basically just be uh, 0 to 7. So there are a few sort of exceptions and sort of different cases that require different logic here. For example, when these, if we're accessing high bytes, so there's like the lower, lower bits, 7 to 15. So that would be AH, for example. When there is no REX prefix, we can access that. When there is a REX prefix, it actually turns into, SPL, BPL, SIL, and DIL. So I want to mark these with another flag, which we'll call XL. So this is sort of, if it's extended, then we want the low byte of this. And then if we're using any of the high bytes, we'll mark them with XH instead. So this will be, AH, CH, DH, and BH, because these are also, 4, 5, 6, and 7. And we can see that down here. If we look in the manual, we've got AH here, so we've got 4, 5, 6, and 7. And then if there's a REX prefix, they become the lower bytes of these registers here. So this actually gets the L on the beginning, and we remove the E prefix, so we've got SPL, BPL, SIL, and DIL. So I'll need these flags. So we'll say that reg is, let's say, 1 shifted by iota. We'll have XL, XH, and we'll also have mem in here as well. So we've got reg, mem, xl, and xh. These are all just flags that we can check. And it'll be useful to have some helper function to check these flags when we're trying to emit machine code. So we'll just have something that is like is, and then we'll say flags is an int64, and then we'll just return a boolean. So we'll say return o.info. We'll mask off the flags, so this is actually a mask, and see if any of those bits are set, basically. So we can say, you know, is reg, is mem, is xh, is xl. We'll also need to be able to use these values when we're encoding, say, the ModRM. So when we looked at the instruction format last time, there's basically this ModRM and SIB byte here. So we've got the mod field here, but then we've got this reg opcode and this RM field. And these are each 3 bits. So this is the selector for the register because it's from 0 to 7. So this is the IA32 registers, you know, AX to DI. And then if we're extending these things with a REX prefix, then, you know, that's when they become, you know, R8 to R15. So the register number is the thing that actually goes in here, because that's, you know, 0 to 7, the lower 3 bits. And so it'd be useful to have some helpers to get that information out of here. So we want the lower 3 bits of the value field, and if the fourth, or if bit 3 is set, that would be any of these extended ones, and if that's set, we know it's an extended register. So we'll just have some more helpers here. So we can say is extended. Is extended will just be a return of whether o.value OX8 is set. And then we'll want some helpers to give us the bytes back used for or the bits back that will OR together to encode the ModRM. So we'll return some byte where we'll say give us, for example, the register and the RM fields. So this will be a return of, so RM is these lower 3 bits here, and the reg field is 3 bits but shifted up by 3. So we want to return o.value, mask off those lower bits, and in this case we just want to convert it into a byte. And then reg is the same, but we're just going to shift it up by 3 bits. And I think that should give us enough information to start working on a generator. I think when we're generating, we'll also need to know, for example, a size. So we'll have some size type as well. This will just be an enum. So we'll just say, we'll have, for example, byte is size iota. We'll have word, we'll have dword, and we'll have qword. So if we have a generator, the generator is going to basically be emitting machine code bytes into its own text byte slice. And we'll, for example, want to be able to call different instructions on here. So MOV, for example, would take a size, then it would take an op1 and op2, and a that's it. Those are operands. We're not going to return anything. If anything goes wrong, we'll just panic, because we should be using this API correctly in the first place. We'll have a constructor, a new generator. And basically we just want to generate text and get the correct bytes out. So we'll create some tests here. We'll have generator test. So this is a testing.t. And the way we're going to do this is we're going to lean on NASM to assemble instructions for us, and then we'll use those as the test cases. So we'll have some instruction here, and then we have stuff that we want to pass into the function. So we'll want, for example, the size, we'll want op1 and op2, and then we'll just have some string of bytes that we want to test for. So for tc range over tt, we'll say we'll say t.run, and the name will be the instruction. And in here we'll say we want to reset some generator text. So we'll have a generator created up here, x64.new generator. Let's see, these need to be prefixed with x64. And this will go into the test package here, and we'll just import all of these so we don't have to use the x64 namespace. And then what we'll do is we'll just switch on the first part of the instruction. So we'll say strings.fields to break up by spaces of tc.instruction. We'll get the first piece of the instruction out, and we'll say, for example, if it's MOV, then we'll call g.mov with the tc.size, the tc.op1, and the tc.op2. Then we'll check, so we'll say if got funct.sprintf, we'll do uppercase hex representation of g.text. So if tc.want does not equal got, then we'll generate an error. We'll say want some quoted bytes. Maybe I won't quote them, we'll just do v, but got this. So do tc.want and got. Okay, and now we need to actually generate some test cases. So for this, I'm basically just going to lean on NASM. So we'll just, in the root of the project, we'll say test cases.asm. Bits 64, because we want it to do 64-bit. And now we'll do some MOVs first. So we'll do AL from CL. We'll obviously want to include the high bytes in there as well as part of the tests. And we'll do, high bytes to high bytes. Then we want to do, so we're doing bytes here. We also want to include some special cases. So for example, SPL and CL, and then we'll do BPL and CL, and then we'll do them both together. So SPL and BPL. So we're just going to test register to register for this time, and then next time I'll move on to sort of memory addressing and things. So I think that covers those. Then we want to maybe look at some extended registers. So for example, R8B and R9B. And then the special cases here would be, for example, 12B and 13B. Because SPL and BPL are going to be special cases when we get to memory operands. And when those are extended, they become R12 and R13. So we'll include those in the cases to make sure we've got some, special sort of edge cases that require more logic. So that's the byte-sized ones. We'll do AX and CX. This is the 16-bit ones. We'll do SP and CX, CX and BP, SP and BP, and then we'll do the extended ones need W as the suffix instead for 16-bit. Then we'll move on to 32-bit. So we got E for the 32 ones, and instead of W here, it's going to be D. And then going further to 64 bits, we've got R and R as the prefixes, and then we don't need any suffix for the extended ones in 64-bit. And then maybe we'll just have a couple of extra cases where we do, you know, for example, a normal IA32 register like AL with an extended one. So we do AX here, and then we do EAX down here, and this one can be RAX. So what we'll do here then is we'll say NASM test cases, and we'll output that to test cases without the extension. Then we'll run disassembly on it. And we can just copy these as our test cases. So we'll just put these in our test table here. We don't need the offset, so that can go. This is going to be the want. So that's going to be the instruction, this is going to be the want. And then we just need to fill in our sizes and ops. So over here we're going to have AX from CX, and this is going to be a bytes operation. So I'm just going to copy this into all of them and then change it. Okay, so these ones are bytes. These ones are 16. So this is a word. Word starts from here. So these ones are word sized. These ones are D-word sized. And then these ones are keyword sized. So let's just change the registers. So for the AH, we've got a special case global for that, which is AH. Then we've got AH and CH over here. Then we've got SP from C. There's BP from C. SP from BP in this case. Then we've got R8 from R9. Then we've got R12 from R13. And we've got A from R13 as well. So these bottom ones are the main 6 differences that we've got here. So we'll just take all of these ones and move them down to here. So we've got SP CX, BP CX, SP BP, R8 R9, R12 R13, and AX R13. So we'll just do that with the rest of these as well. Let's see, 32-bit. Okay, yeah, I need to go down one more. So it's actually these ones here. Okay, let's try this again. So we got SP here, down to bytes here. Then we'll take these ones, skip the first one there. That gets replaced with those. These ones start down here. And then the same for the keyword. So I think those are all correct. And these are test cases for MOV register, or MOV reg to from reg. So if we run these, we get lots of errors because we're not generating anything right now. So basically, we're just going to go and look at the encoding for MOV instructions. So we'll go to chapter 4M, and we'll look for MOV here, and we're just going to be copying the output of NASM, because there are actually some redundant ways to encode these things. So for example, in this case, we've got RM as the destination, so this is op1, and we've got a register as the source, and this opcode is 89. But if we look down here, we could also encode this. We've got R as the destination and RM as the source. Because RM means register or memory, it means that we could actually use either of these opcodes and they would both be correct. NASM is outputting 89 for the register to register case, but we could just as well use 8B if we wanted to, for example. So we're just going to follow what NASM is doing so that we can use it for test cases. It doesn't really matter which way around we actually do it though. The other thing to notice here about MOV though is that the bytes instructions actually use a different opcode. So in this case, the opcode for a byte MOV is 88, and then when we are not using a byte, so if it's 16, 32 or 64, we actually move up to 89 for all of these ones here. And then the same thing happens with the other redundant encoding, which is that it starts at 8A for a byte, and then it adds 1 for anything that's not a byte. So we can start the opcode as being 88, and just say, for example, if it's not byte-sized, we'll just add 1 to the opcode. So, so basically the bytes instructions here, we can see there's 88 in all of these. And then suddenly, after it's not a byte anymore, it moves up to 89. And then we've got 66 here, which is the operand override prefix to go to 16 bits, because the default is 32 bits. Then the 32-bit ones don't have any prefix on them, except for when it's needed for extended registers. And then the keyword ones have a lot of REX prefixes, so this 48 is just saying, it's a 64-bit operand size, and then in the case of extended registers, that gets ORed with some other REX flags to make it 4D instead of 48. So we'll basically just start generating this stuff. So we basically said that we used, we're going to use an opcode of bytes 88. And we'll say that if the size is not a byte, then we'll just add 1 to the opcode. And then what we want to do is just append to the text here. Appends to g.text the opcode. So if we rerun this, we're now generating the opcode, so we get 88 for all of the byte ones, and for anything that's not a byte, we get 89, which is correct. But before that, we also need to tell whether we should be using an operand override prefix. So maybe I'll just put a const over here again. We'll have const operand override, or operand-size override. And this will be 66. So we'll say, for example, do a switch on the size. We'll say in the case of bytes, we'll do opcode ++. We'll say that in the case of word, we'll... oh, this is not byte actually, so we should keep this in a separate if up here. So if the size is not bytes, then we'll do that. If it's word, then we want to append the override before we do the before we emit the opcode. So let's actually just change this to an if for now. If it's a word, then we want to override to use 16 bits. So that gives us, for example, here we got 66 4589. So this obviously has a REX prefix as well. But here we've got 6689EC, so this is 6689. And now we need a ModRM to encode the selection of the registers. So after the opcode, we want to do ModRM. So let's have a ModRM bytes here that we encode. And perhaps what we'll do here is we'll have some var prefix, which can be bytes. And then what we'll do is we'll just say that prefix equals operand-size override. It'd be nice to keep all of the appending down at the bottom here. So we'll say, for example, if the prefix is not is set, then we'll append the prefix here. Then we'll say, you know, for example, if and then we'll do, so after the opcode comes ModRM, and we need to set different things based on what's going to go on here. So we're just doing register to register at the moment. So in x64 over here, we'll just have some value for the addressing mode. So in the ModRM, if we go and look at the encoding tables and things, so mod is the 2-bit field, and mod can be one of these 4 values here. So if it was 0, 0, that would be in a nibble, that would be 0, 0, 0, 0. Then we get 0, 1, 0, 0, 1, 0, 0, 0, and then down here is 1, 1, 0, 0. So this is 0, this one is 4, then we've got 8, and then we've got C here. So 0, 4, 8, C for the mod field. So that's the addressing mode. So if we say, for example, address direct would be the registers. So this could be, this is C because that's 1, 1, and then 0. So if we format it like this, then we can just do some bitwise OR to build the mod bytes. So we'll have let's see, indirect addressing, which is when we use the register as part of accessing memory. And this has one with a 8-bit displacement and one with a 32-bit displacement. So in this case it's 0, 0. In this case it was 4, 0. And in this case it was 8, 0. And then C0 for the direct case. So we're just going to use direct in this case. But when we get to memory operands, we'll need to actually select the correct addressing mode. So at the moment, ModRM is basically going to be address direct, ORed with some, you know, reg field, ORed with some RM field, because it goes reg then RM. So RM is the low 3 bits, and then reg is the middle 3 bits. And those come from the operands, because the operands have the register number in them. 3 bits is 0 to 7, so that's 8 possible register selections in IA32. That would be, you know, AX, CX, DX, BX, SPBP, and then SIDI. And then those can be extended with REX if needed. So what we'll probably do here is we'll say, for example, op1, or sorry, op2, because we're following these tables at the moment, assuming RM is the destination. So these tables are set up to assume that RM is the destination. Or, you know, it's set up to assume that RM is, you know, operand 1, which in the case of MOV is the destination. So this is the destination, and this is the source. So op1, we need the RM from op1, because that's the destination, and we need the reg field from op2, because that's going to be the source. So reg field is from op2, and RM field is from op1. So that's where these come from. So we've got the lower 3 bits is RM, that's going to be from op1, and then the reg bits come from op2, and that all combines into the ModRM bytes to select the operand registers. So let's just see what I've missed here. Nothing much, but we are actually encoding some things correctly. So what are we missing here? We've got SPL, so this is a case where we need a REX prefix because we're actually accessing the lower bytes of a register that you couldn't access a lower byte from in IA32. So because this is a 64-bit extended sort of register selection, this is in place of AH. So instead of AH, we're doing SPL, and in that case, we need a REX prefix. So the REX prefix here is 40 because the upper nibble of REX is hard-coded to be 4. So if we look at the REX prefixes down here we see that you know, this high nibble here is hard-coded to be 0100, which is a 4, and then we've got you know, W, R, X, and B. So if this is 0, then none of them are set. If we were doing a 64 bits operand, then this would be set, and that would be 8. You know, if this one and this one were set, then it would be 9. I did see a D in there, so that's probably what is D? D is like 13 or something, right? So we've got, you know, 8, and then we've got you know, this one and this one is probably how it is, because this is 12 plus 1 is 13. So this would be D. So 4D in the REX prefix would be that we're you know, using R to extend the ModRM reg field. So R extends reg, and then we would be using, you know, B here to extend the RM field. And then it would be using W to set a 64-bit operand size in that case. So we've got W, R, X, B. So we'll just go and encode all of those things into some constants over here. So we've got REX. REX itself is just 40, so that's just with no bits set. We'll then have REX W. Maybe I'll do this one on the bottom here. So this one is 4, 8. So with W, R, X, B, R is 4. Then this one is 2, and this one is 1, because they're all just the different bits here. So we got B here, and we got X here. So 64-bit, extend the register field, extend the SIB index field, and this one extends the RM field, or the base register field in the SIB byte. And then this one, we're not extending anything necessarily, we just need it so that we can select, for example, SPL. And so that's where this XL flag is going to come into play. We're going to say if it is XL and we're, you know, on a byte size, then we will, you know, need REX, for example. So REX always comes before the opcode. So we'll say REX here is going to be a byte. And what we'll do is we'll do a switch on the size, because depending on the size, we're going to do different things. So in the case of byte, if op1 is XL, or op2 is XL, then REX or equals just REX. And in the case that we've got a keyword size, this is a 64-bit operation, so we should do REX W. Now before the opcode, we'll just do the same thing as prefix here. We'll just say if REX is set, then we will basically just append it. So that took care of the SPL things. Now we've got some extended registers here. So we need to know if they're extended, and we're saying that the op1 is RM. So that's going to be the B, REX B, So let's say we've got if op1 is extended, then rex or equals rex b. And if op2 is extended, then that's going to be r, because op2 is the reg down here, so that extends reg, and op1 is rm, and b extends rm. Okay, so that actually passes all of the tests now, so we are successfully emitting the correct machine code for all of those register to register moves. So I think I'll have a look at memory access next time, because otherwise this is going to go on for a bit too long. But there are a couple of things that we're going to have to pay attention to, because when we get into, memory accesses, suddenly the order starts to matter a bit more, and we're going to need to pay attention to these different opcodes and things. So yeah, we'll just see how we're going to deal with that next time.